Welcome everyone to RIoT 49, the competitive edge. How edge computing takes business to the next level. I'm sure we've all heard edge computing as this buzz tech word, but what does it really mean? From latency to bandwidth, one thing experts agree on is that the majority of future innovation and growth will happen at the edge. Tonight, we're excited to hear from 3 experts to get their take on where edge computing is going. Like all of the 48 RIoTs before it, today is made possible by the support and partnership of RIoT sponsors. Because of their generosity and engagement in RIoT, we're able to bring you today's event for free and support entrepreneurs and economic growth across the U.S. So before we get to the main event tonight, a couple of things to put on your calendar. RIoTs 50 and 51 are coming up on February 23rd. Join us at RIoT 50 as we continue to explore DEI. At this event, we'll be examining accessibility through 2 lenses, the digital divide and physical and cognitive disabilities. Bright and early, on March 16th, we have an awesome event called Technological Innovations in 22401. At this event, we'll be hearing from some friends in Fredericksburg, Virginia, some small business owners and technology partners to hear how leveraging different kinds of technologies makes their small businesses fly. We ask everybody to keep your eyes and ears open for some exciting announcements from RIoT. We'll be launching cohort 7 of RAP soon, and the whole team is just blown away by this cohort. And last but certainly not least, if you're interested at all in augmented reality and love a challenge, you might want to follow us on social media at RIoT on Social. So how's everyone enjoying tonight's platform so far? Some of you may remember back in April of 2020, RIoT launched Mission R with the goal of supporting entrepreneurs who were actively working on a solution that addressed one of the many problems society faced during the early days of COVID. One of the teams that went through Mission R and a success story is Socialize. Rod, John, and Paulo saw that existing virtual platforms were missing an important factor, being able to network. They went to work to develop their own platform, and RIoT is thrilled to be able to help beta test it during the event. So thank you all for your patience and willingness to participate in a bit of customer discovery. The Socialize team is on tonight monitoring the chat for any bugs or questions you might have. So we ask everybody to play around, try out some features, and explore. After the event, we'll be sending around a survey to gather some feedback for the Socialize team, and we'd appreciate all of your support and participation. A few housekeeping items for the event. The main stage will be recorded and uploaded to RIoT's YouTube page. We ask everyone to keep yourselves muted during the presentations, utilize the chat window for any questions, and we encourage all of you to visit our exhibitor booths. You'll see them on the left side of your screen. Speaking of our exhibitors, thank you tonight for taking part in this, and please take a few moments to stop by. These are some great companies doing really amazing things. Now, what you've all been waiting for, let's get started with tonight's main event. Our first speaker tonight is John Cowan. I'm very pleased to introduce him. John is co-founder and CEO of Edgex. John is really Edgex's visionary and strategy leader. He has over 20 years experience leading early stage companies and developing talented teams. John, welcome to the main stage. Hey, John, how you doing?
Good. How you doing?
Great. Why don't you go ahead and pull your slides up? I just want to remind everyone that Edgex has an exhibit booth, so please stop by to learn more. And if you have questions for John, please put them in the chat box, and we'll get to as many as we can at the end of his show. So, John, take it away.
Great. Can you see my single screen okay?
You're looking great.
Awesome. Fantastic. Well, it's a pleasure to be here. Thank you so much for the invitation. I always enjoy going first amongst the group of speakers because it provides the opportunity to get as much out as you possibly can and set the stage for what I think is an important agenda to discuss around edge computing. So I'm pleased to introduce Edgex, which is a Raleigh-based early stage company focused on tackling the edge and all the challenges therein. I'm going to provide a little bit of an overview today of the way that we see the edge and the edge challenges and our unique approach to trying to solve some of those challenges for developers in the Internet of Things. So just to kind of set the stage as a bit of a reset, if you will, on kind of why we're here, it's helpful to kind of frame this as the way we describe the IoT, right? To us, it's the fourth internet. For those of us that are old enough, like me, to have built a career dating back to the early 2000s, it's kind of hard to imagine that anything could have had a greater impact on the industry than cloud computing, but we would be wrong. The cloud computing era was all about building internet-based software designed to connect the 13 plus billion odd people and things on the internet. But over the last several years, the nature of internet software has begun to change. It is moving out of the abstract world of spreadsheets and blogs and games and social media systems and platforms and into the real world. And in the real world, internet software is beginning to make critical decisions based on pattern recognition and signal interpretation and other things. And many of these decisions involve split-second timing that can mean the difference between things like profit and loss, wealth and bankruptcy, efficiency and waste, or even life and death. And it's when you see the future of the internet this way that you begin to develop an appreciation for the fact that IoT as a concept in an era is really going to dwarf everything that came before it. It will be bigger than everything that has come before it in the computing paradigm by orders of magnitude. Humans and human interaction will no longer be the dominant customer or consumer of compute and storage resources. In the IoT era, consumption is going to be driven by the connected apps and devices, and there are way more of those than there are humans. And that's what makes us excited to dig in and look at some of these challenges around IoT. So today, though, I mean, if we live in the world of here and now, what I call the third generation of the internet, this is how things look. This is how the world of web services and cloud computing kind of looks to you. Data and content is stored and served up to us in centralized cloud computing data centers. And through those providers or service providers or our own hardware or infrastructure, we're able to consume and do the things that we're even doing today, even this platform like Socialize, for example. For the era of web services, this works just fine. And for most things that I do today, I can tolerate the latency that exists between where I am on the internet and where the computing resources are that I need to use. And for this reason, the notion of cloud computing is likely here to stay for the foreseeable future. It works pretty good. However, there's a bit of a problem. In order to enable the next generation of internet software that I've described, high-performance computers are going to need to be located as close as possible to the things that generate the data and information that informs the models that create the events and make the decisions. And this is really where this concept of edge computing becomes super important. This notion that proximity matters, that I need to put the cloud as close as possible to where data is being spewed from sensors and devices and things all over the place, right? It's all the rage of late. Obviously, everyone's heard of edge computing. Latency matters a great deal in IoT, though, because we can't afford to have, say, an autonomous vehicle taking its time to tell the difference between a pylon and a pedestrian, which will require dependency on multiple real-time sensors, not just the sensors on board the vehicle itself. So to illustrate the gap that exists, I've highlighted some typical round-trip times in various AWS regions and called out the latest research involving, say, driverless vehicles. Their maximum latency tolerance is less than 5 milliseconds, whereas centralized cloud computing data centers are up to 40 times off that mark. That is a very big problem to solve. And so it seems easy and obvious and logical that let's just put cloud computing closer to where data is generated. If it's too far away, let's just put it closer to where data exists. That's our big idea, right? Well, the ambition of Edgex, which is highly simplified for the purposes of a vision statement, is to basically put edge computing everywhere within 1,000 feet of every connected thing. We think that a high-performance computer needs to be located that close to every connected thing, device, machine, what have you, that is creating data for processing. And so when we set out to solve this problem or tackle this problem, our first inclination was to just go back to what we know, the cloud. Right? Today, when most people hear the words edge computing, they think of something like this picture. The cloud is the center of the universe. It certainly is the center of my universe for the last decade plus. And the edge is more or less extending the cloud in some way to be close in proximity to those users and things. That's also the way that most architects have thought about the edge problem. That is, they've been working on extending the tools that we've been building for the last dozen years or so, virtualization, containers, Kubernetes, etc., and trying to make that all work at the edge. And in general, the way that we've tackled complexity in the cloud is with orchestration, right? You can take whatever name you like. There's a lot of nice names that people give these things, like schedulers or brokers or autonomous infrastructure or what have you, but they're all extremely complex. In the last 10 years, we've made great strides at improving orchestration. We know the names in the industry, right? We orchestrate database clusters, whether they're relational or NoSQL, et cetera. And we orchestrate our software deployments as containers and virtual machines. DevOps is wonderful. It's awesome. So it's natural that we want to take all of that work and all of that expertise over the last 20 years and build something better with better infrastructure at hyperscale and kind of just move it to the edge. But in fact, when we first started out our ambitious project at Edgex, that's exactly how we thought of the problem. So we're no different in that context. The issue, though, is that it kind of doesn't work, right? So there's a lot of reasons that we might say that today's cloud architecture is not a good fit for the edge. But speaking from experience, the root of those reasons is that the cloud's problematic key assumptions around centralization and permanence. Okay, that might strike some of you as a wrong-headed thing to say, maybe even sounds a little bit like heresy in the cloud, but it's something that brought us a lot of great agility, and we all love the cloud. But the notion of cloud is built on permanence. We build and deploy applications to static environments, even though it's this big amorphous thing called the cloud, right? But now we're talking about the edge. In the cloud, your data center doesn't move around. In the cloud, racks don't disappear in one data center and suddenly reappear in another. But that's kind of exactly how our IoT applications need the cloud to behave. It's when we examine this uniquely edgy problem of ephemeral, transient code and data that we begin to understand the nature of the beast, that the cloud architecture, the way we know it, doesn't really work under those constraints. From a developer side of things, we love the cloud. We want it to look like the cloud, but the gears of infrastructure that we've been used to, they have to be assembled and turned in a different way. And moreover, we need to maintain all that we gained from public cloud computing in the sense of multi-tenancy, right? We don't want to sacrifice that. So our first step to kind of solve for this distributed application development challenge is serverless, right? And we at Edgex are firm believers that serverless is going to dominate the IoT world as it becomes more the mainstay, because serverless is the closest approximation to how we actually build traditional IoT apps. They need an event developer framework. And that's what serverless gives us in a simple and beautiful way. It's an event-driven world. We don't need everything everywhere at all the time. We just need it where and when it actually needs to be there. And I think it's kind of wonderfully ironic that the ultimate cloud technology, serverless, invented by the grand poobah of cloud, Amazon Web Services, is actually going to be cloud's downfall when it comes to the edge, right? It's not to say the cloud is going away. I want to reiterate that, or disappear. In the next few years, though, what we think of as the cloud today, these big centralized data centers and infrastructures, are going to become a lot less important when we're building the next generation of apps and services at planet scale. So serverless is, we think, a big piece to solving the challenge of making it possible to scale apps at planet scale. But how do we actually make serverless exist and run without all the complexity? For guidance on this, it's helpful to remember the creators of the internet. And of course, I'm referring to Al Gore. If anybody denies that Al Gore created the internet, we're going to have a separate conversation, because he did. We're still using the technology that the creators of the internet developed over 40 years ago. They lived in a world of constrained resources. How did they make the internet work with such resource constraints on internet routers? Simple. Small is beautiful. They created protocols which could deal with state, and they made state really small. And that got us to thinking at Edgex, what if we could build something like a routing protocol for serverless that ran everywhere? And what if we could make serverless functions appear, execute, disappear in response to protocol states? What if we could do that same thing for data, right? With actual data. In other words, what if we built a truly distributed system, and instead of a complicated orchestrator the way that cloud purveyors would like us to try and do. This is exactly what EdgeNet does as an introduction. EdgeNet is our patented peer-to-peer content address storage network that uses a gossip protocol to make code and data available everywhere and anywhere. And by deploying EdgeOS, which is the Edge operating system stack, users can boot up and join any peer-to-peer network of computers and deliver the idea of a truly distributed edge cloud network. So I've intonated at one of the other challenges that exist in cloud at the edge being security, right? So back in the early days of our Edgex project, what we tried to do is borrow from the blockchain technology era. You know, we were fascinated innovators when it came to the blockchain era because of things like trustlessness and immutability. In fact, the first prototype of our EdgeNet platform was built using Ethereum as the underlying model to kind of decentralize trust. However, we quickly discovered that the consensus models that made blockchain so fascinating made it untenable for use to validate large volumes of data and code in any kind of reasonable time frame. It just wasn't right for, you know, the kinds of plumbing that would be needed to move and process lots of large volume data sets and code. And so that's why we designed something called Edge Notary. So just to kind of introduce this a little bit, if I have a piece of paper that I want to have validated in any court in the land, I would take that piece of paper to a designated human called a notary, and that notary is going to attest to the document's authenticity by placing their stamp and signature on the paper. We all know this. We've done this many times in interacting with the court system of the land. And that also got us to thinking that what if we could actually achieve the same thing but digitally, using code and data on the EdgeNet? So we developed this thing called Edge Notary, which, as the name would suggest, creates the ability for code and data to be cryptographically validated on the EdgeNet. Now, why is that important? Well, we think it's actually tantamount to solving the huge problem that IoT faces, broadly speaking, because, as we talked about earlier, IoT apps are taking on a much more serious purpose than traditional web services apps. And the last thing you'd want is for some nefarious actor to modify a line of code or take control of an autonomous machine or otherwise cause a disruption. So using Edge Notary provides a way for the developer to verify that the code and data executed on the network by a thing or a device or another code function is in fact true and has never been modified or altered in any way. Kind of preserves the value that we see in the era of blockchain without the performance hang-ups and limitations of technologies in the recent times. So before I wrap up, I'll just highlight a couple of use cases because obviously this is a lot to digest and it's still pretty high level, but just to kind of wrap your mind around, you know, where this goes and some of the things that we're working on here at Edgex that we think are very important IoT use cases. I'll first illustrate the work that we've been doing in the Department of Defense sector of IoT, the Internet of Military Things, as our partners like to call it. Our partners are using Edgex technology to build something that they refer to as the Edgex Federated Warfighter Tactical Edge Cloud, which is an amazing concept and term that just kind of rolls off the tongue. If you've spent any time in DoD land, you know that they like to come up with long-winded acronyms for names and things, and that's all good. But the idea is to take our entire technology on a geofenced basis and deploy it across a network, an edge net, if you will, that spans the HQ through the forward operating base all the way to the warfighter edge, the theater of battle, say, for whatever military group or department happens to be deploying an edge net. And the concept there is to solve the problem that the DoD faces, in that it's very difficult to get all of the advanced algorithms and solutions that they've created to be real time, to be highly tactical and useful to the folks that are on the ground, the boots on the ground, as it were. So an example of this would be, for example, gunshot detection in the field of battle. How can a warfighter tell in real time the difference between a car backfiring, a firecracker, and an AK-47? And how can they triangulate the potential distance or other vectors affecting a threat response? Well, to do that today is very difficult because the warfighter obviously doesn't have a giant data center on his or her back. So a lot of that solutioning, a lot of those intelligent algorithms have to be processed kind of in post-mortem. But by extending cloud services down to the edge across ruggedized compute form factors, what we can actually do is bring the cloud to the warfighter. Right? Hence the federated warfighter tactical edge cloud solution that we believe and our partners believe is kind of part of the base of the future as we think about IoT in a military context. Finally, in my last few seconds here for the time I have before I'll take questions, I'll highlight another use case, which is a little more near and dear to us, and that is urban IoT. So, and specifically, I'll highlight one of our example use cases in traffic. So, by putting ruggedized form factor edge computers in locations like the street corner, for example, and deploying EdgeOS and federating a group of computers in an urban environment, we can begin to effect real IoT solutions involving connected and autonomous vehicles. And the solution that I'm highlighting on our screen here is real-time pedestrian detection, where in the classic IoT framework between sensor, processing, and actuator, we're taking video as a sensor data from a camera in an intersection, processing that on the edge net, comprised of those high-performance computers down at the street level, and producing information that's useful traversing V2X networks into heads-up display as a UX for connected and autonomous vehicles, but also into advanced predictive analytics for traffic control. We see these kinds of solutions as the future, for example, of things like EMS and traffic routing and traffic control, and even the identification of engineering fixes in dense urban environments, whether it's a sinkhole or a pothole or a downed light or what have you. So that's a bit of a mouthful, and I appreciate you guys being patient while I raced through as much content as I could cover in 15 short minutes. I'd like to thank you for your time, and seeing is believing. Go to edgex.io/beta, sign up today, and we'd love to expose our platform for developers of all ilks. Help us build the future. Thank you very much for your time.
Thank you, John. That was excellent. Really exciting to hear where Edgex is going. It does look like we have a few questions, so bear with me. So Chris, our Western Side Partnership Director, has a few really great questions. He wants to know, where can developers go to learn more about the Edgex platform? So
Edgex.io is the first and best source to consult and get onboarded with our technology. One of the things that we covet at Edgex, like a lot of developers, is great documentation. So we've borrowed from a lot of our mentors, if you will, that have come before us in realizing that good documentation creates good developers and good experience. I would invite anybody to come to edgex.io, get in touch, and tap into our resources to help you learn and begin to build serverless apps, distributed apps.
Awesome. I see Chris put the link in the chat box, so thank you, Chris. He did have one more question. He'd like to know, what are the minimum system requirements for an Edgex Edge server?
So because EdgeOS is it's a free BSD build, so it is extremely small. I mean, we've deployed it on small as a Raspberry Pi. It is an OS install, so bare metal virtual machine doesn't really matter to us.
Okay. Gabriel has a question. What happens when a node is off? Will it get the data when it goes on again? Where is the data stored or relayed?
Well, so this is another sort of clever invention. Look. Yes, we invented the EdgeNet, but at the end of the day, we borrowed heavily from what we know and our experience in building the internet in the last 30 years. So the way that EdgeNet works is as a peer-to-peer network. So what happens is if one node drops offline for whatever reason, then code and data is instantly passed to the closest available proximal node thereafter, the next node in line, if you will. So that way, we never drop a packet, we never drop a job, we never create outage or disruption for the kind of code and data that is so mission critical in IoT.
So Tom wants to know, are you more competing or complementary to 5G networks and the embedded compute that will be in each of those network nodes?
Complementary. So if you think about, 5G is an interesting dynamic, right? So 5G doesn't solve the latency problem, right? So, a lot of folks say to me, well, yeah, 5G, well, I don't have to worry about computers at the edge or these kinds of things because 5G is going to solve that for me. The reality is that 5G is really just about bandwidth. It's not about distance. Whether I have the most robust 5G network or not doesn't bear any consequence on the fact that I'm not solving for the speed of light. In other words, computers still have to be proximal to where code is generated in order to achieve those ultra low latency times for code response, for execution response. And so from that context, though, that it's very complementary to what we're doing, because obviously marrying an edge computer running Edge OS that's connected to a peer-to-peer network dovetails beautifully with anybody that's building a private or public 5G network.
So Mary has one question. She wants to know, what protocols do you use to receive and send data to the nodes?
Sorry, can you say the question one more time?
Yeah, absolutely. What protocols do you use to receive and send data to the nodes?
So out of the box, ATP, MQTT, pretty much any of your typical IoT protocols are supported out of the box to write data to the EdgeNet itself. But HTTP and MQTT are the two predominant protocols that we've seen in our early rollouts with enterprise customers.
Awesome. Well, John, thank you so much for being with us today. This was a really great talk. I enjoyed it a lot, and I know our audience did.
One quick question I just want to highlight there, Amber. Somebody asked whether there's a relationship between Edgex and Edgex Foundry. No, there is not. Edgex, I one time, my CTO kind of slapped me for this, but at one time I was at an event and somebody asked that question. I said, no, we're not related to Edgex Foundry. We're the cool Edgex. So.
Well, everybody remember that. These guys are the cool Edgex. John, thank you again. We really enjoyed it. And everyone, just so you know, we're going to take a very short break while we get our next presenter up and running. So feel free to test out the platform and visit some of our virtual booths, especially the Edgex one.
Thanks, Amber.
Take care.
Take care.
Everybody, we're back with our second presenter. Give us just one more second. There we go. So up next is Christian Solomine. Christian is another veteran in the IoT space. He has over 20 years experience and one of the founding members of the IoT World Alliance. Christian, welcome to the main stage. We're excited to have you and really interested to hear about your insights.
I'm just starting to share my screen and I'll get going here.
You got it. And just a reminder to everybody, if you have questions for Christian, please put them in the chat and we'll try to get to as many of them as we can at the end of his presentation.
All right. Can you see my screen okay?
Looks good on my side.
All right. Well, excellent. Well, thanks everybody for joining. The topic of my presentation today is the future of predictive analytics. And it's great that John went first, because this really builds upon the use cases of AI, machine learning, edge, and 5G, and I'll talk about that. So we're going to go through AI, predictive analytics, some practical industrial IoT applications, and the impact that 5G and edge will have on the industry. I'll then go into a Q&A session. I preceded with a couple of questions that I always get asked about these sorts of things, but would love to get your feedback in the chat, and I'll do my best to address those. So as Amber mentioned, I've worked in the IoT space for about 20 years. I've worked for some wireless telcos like Rogers Communications and Telefonica. I was one of the early employees at Jasper Wireless, a service delivery platform for IoT. I worked upon the IoT World Alliance. That was a consortium of mobile network operators that were working on a one SIM solution, so you could build once and deploy in multiple locations. Currently, I'm a board advisor at IoTM. That's an AI-based telecom expense management firm that also works on data analytics for industrial IoT applications. And previously, I worked at Uptake. It's an AI and machine learning platform for predictive analytics for industrial IoT applications. I currently do consulting work for sales and go-to-market strategies, primarily focusing on wireless and IoT-based companies and startups. So what I'm going to talk about today is reducing unplanned downtime through the use of predictive analytics. So basically knowing what's going to break on your industrial asset before it breaks. There's a number of different stages that many businesses can be at as it relates to predictive analytics. The first being regressive. That would be you're running your asset to failure. That could be a wind turbine, a locomotive, a manufacturing press, a long-haul truck. Then organizations will work on reactive. I'm using my asset, something breaks, and when it does, I take it out of service and I fix it after it breaks. Most recently, people were doing preventative maintenance, and that was basically following an OEM or other type of schedule and replacing subcomponents of the electromechanical system before they broke, but based upon a predetermined interval, whether that was hours or miles driven. But where we're at today is predictive. So we are taking data feeds from the subcomponents of an electromechanical system, running it through a series of AI and data science models, and predicting when those subcomponents are going to fail before they fail. In the future, we'll take this even further to be self-sufficient through the use of edge technologies where the actual asset can determine it's going to fail. It can call in and basically say, this part is going to break, and order a new part, and or optimize a maintenance schedule where I'm pulling the asset out of service, doing my planned maintenance as well as the predictive maintenance elements all at the same time. So your application might be anywhere along the spectrum, but today we're going to go deeper into predictive. Before I do that, how I define AI is basically things happening that a human could do, but in an automated fashion. As it relates to industrial IoT, that's a combination of the IoT device itself and the sensor information you're getting, a series of machine learning that's being applied and enhanced over time, and data science with AI at the middle. Recently, we have folks that are coming out and becoming AI engineers. They need to work with industry technicians to get a better feel for what's happening with their assets so they could better write applications to solve for predictive analytics. But combining these two in the industry is what we're seeing called industry data scientists. So these are the people that not only can write these applications, but truly are SMEs in terms of what subcomponents of these assets and systems and how they work. AI. So most people think AI works like this. We have data, we create some models, and we get a business result. And at a very high level, that's exactly what's happening. But there's a lot more to what happens in the background in terms of how AI actually works. In the yellow block on the left-hand side is the piece that's really critical to making any system work properly, and that's on data cleansing and homogenization in the system. The second component of any successful system is the model training. So you get good data into your system, you build some models, and you reinforce those models with training elements. Now that may be bouncing back the results from your models to a work order system, seeing if what you're predicting to fail actually translate to real life, and then the efforts they take on that data, how that cycles back into your overall model. So you have these circles of information basically building upon themselves to ultimately achieve a good business result. And for industrial applications, that's typically reduced downtime. I'm going to go into an example here for automotive. So again, building upon what John was talking about, but this is utilizing the use case of a diesel engine, typically found in a Class 8 truck, an 18-wheeler for long haul. We're pulling in real-time telematics data, typically through an IoT device connected to it. Those devices are increasingly becoming more edge capable, so there's a lot of pre-processing happening on them. We're also pulling in enterprise work order data. We then augment that and overlay it with contextual information like weather or other operating conditions. You then take that information, run it through a series of AI engines. Those could be for filtering out the noise, taking out that erroneous information that I spoke about on the other slide. It could be identifying anomalies. It could also be used to predict failure. So the outcomes of these are better decisions. So we're reducing noise. We're consolidating the shop visits and or the downtime events that we're utilizing to improve that asset and or fix things, but we're also getting advanced notification. So we're fixing before failure and at the same time minimizing those downtime events. This is an example of a diesel engine. These are typical data elements that come right off the J1939 protocol. All of this information is free and available to anyone who wanted to touch it. But in order to get this information back, you need some pre-processing. You need to query the codes on the engine, and then you need to transmit that data. That's why Edge will be so important, because today on most wireless networks, you cannot stream the gigabytes of data that can be flowing off the engine. So you're basically querying, doing some edge processing, and then passing back that result over the network to be able to do some things on board as well as pass back for historical analysis. So in summary, on the AI-based component, really what we're looking to do is find that signal in the noise and provide advanced notification to prevent unplanned downtime. When you're getting information from a vehicle, from any other industrial asset, you'll get things such as fault codes, historical work orders. And on an individual basis, that's easy to take a look at and determine. But when you multiply that by a large fleet of assets, maybe it's 1,000 wind turbines or 10,000 long-haul trucks, that data can become overwhelming. So what AI allows you to do is find patterns throughout this data set and determine appropriate courses of action. I'm going to give two real-world examples now. What does this really mean from a practical perspective for industrial IoT? The first one is a correlation. So this is basically comparing engine speed, engine oil temperature, and engine coolant temperature on an industrial asset. Typically what you would see is as engine speed goes up, the temperature of your oil goes up, and your coolant also goes up because it's pulling heat away from the engine to cool it. What I'm highlighting in the white circle in the upper right is a severe deviation from the engine coolant temperature. Now, the dotted lines that run horizontally are the OEM thresholds for when they would fire off a fault code. That would be a reactive result, and that would typically mean that vehicle has already broken down, there's steam spewing out of the engine, it's pulled over the side of the road. But through the use of edge processing, as well as AI, we can see this deviation well before it hits a manufacturer threshold. In this case, there was an issue with the coolant circulation in the vehicle. The operator was able to pull that vehicle off the road at the next service interval, fix the issue, and they never had an unplanned downtime event or roadside breakdown. This example is for cranking voltage on a battery. As many people know, over time, batteries tend to degrade. When they crank the engine, there's a whole bunch of millisecond level events that show cranking voltage. Now, with edge processing, you can take that information, you could do some initial analysis, but you also want to pass it back to your host server because you could also do trends. Here you see the gradual degradation of a battery over time. And the yellow vertical bars are when repair orders would typically be sent in. But again, that's typically when a vehicle doesn't start at the beginning of the day. By analyzing the trend, you can actually see that type of decay, much like radioactive decay, and you'll know at some point in the future when that battery is ultimately going to fail. But that 1 week, 2 week advanced notification is critical for businesses because that allows them, one, not to have a roadside breakdown, but two, build in that battery inspection along with other things they were going to do anyway. That particular unit may be due for an oil change at a service interval. So what they would do is they would optimize their shop schedule and also take a look at that battery at the same time that they're changing the oil. Now, deployment options. There's many different ways about going about this. You can build your own solution, so you could develop your software, build your own infrastructure, and hire your own data science team and build that out. That's high risk because it costs a lot of money, and if you do it wrong, you could have significant costs. However, on the flip side, you can have ultimate control over what your application is. Next level down is buy a toolkit. So a little bit less risk, a little bit less cost, and there's a ton of different providers out there that will allow you to build out a data science team and build your own models on top of someone else's platform. Or you can basically work with a ready-made solution, let the provider do the heavy lifting, lower cost, sometimes less flexibility, but also lower risk. So I'm going to jump now into a couple of questions, and then we'll open it up on the chat. But these are two that I routinely get asked when I work with industrial IoT companies. The first one is, why are so many companies stuck at the pilot stage of AI projects for IoT applications? In my opinion, there's two main reasons. The first one is availability of good, clean data. There are many different data sources that you may want to pull in. Many of these data sources are unstructured. Sometimes you have horrible anomalies that may impact your analysis. So working on cleansing and getting that data into a useful format is one of the toughest challenges for a lot of industrial applications. The second piece, in terms of why some of these projects either fail or don't get beyond the pilot stage, is the ability of the organization to operationalize what the system is telling them. If you're going through a digital transformation exercise, being able to modify your work processes and your internal operations are critical, because these systems are going to tell you something in a very, very different cadence than you've ever expected it before. So if I'm able to tell you from an application perspective that this truck that you've rented, maybe it's on a 2-month rent, is going to break down in 3 weeks, how do you change your business in order to get that vehicle back out of service when it's on an active rent to a client? Those sorts of operational changes really need to be thought through up front, because the conclusions that the system may drive would change the way the business works as it is today. The second question that I routinely get asked: what additional enabling technologies are required to fully enable Industrial 4.0 to materialize? And I kind of talked through a couple of them already. One is the edge element. Because so much data is available on an industrial asset, having edge processing is critical, because you can't just stream gigabytes upon gigabytes of data back. One, it's inefficient. Two, there's massive latency. And three, in large part, it's unnecessary. So the increase of 5G networks will definitely help with that. But having edge processing available, working hand in hand with 5G, will be the additional enabling technologies that allow this to materialize and thrive. So Amber, with that said, I want to open it up to Q&A. I think I've got about 10 minutes or so, and just want to see what sort of information we're getting in the chat.
Yeah, absolutely. So it looks like we have one question right now. Chris has a question that says, where is there the most need in predictive analytics at the edge? Is it computing power, clean sensor data, experts in the domain? What do you think?
I don't, all of the above. I mean, the most important thing is, if you're getting a ton of sensor data, that your edge device can strip out and do some basic level processing as computing horsepower gets better out in the field. I can't overstate the requirement for industry SMEs. When I worked at Uptake and a lot of other companies, we would work with diesel mechanics when we were building our data science models, because the nuance of what is happening in a living and breathing engine, from battery and electrical elements all through the after treatment system, you can build the best model that you like, but without having that industry SME input into your models, you could miss some really critical elements that even machine learning wouldn't pick up on. So I think it's a combination of having that strong edge processing, good backhaul on your network, but also having skilled, industrial data scientists, as I referenced in that slide, are critical to having a successful application.
Oh, that's a really great point. Tom has a question for us. He'd like to know, how do multiple edge AIs get aligned if they move from original training data, but then diverge at different edges? Does it make sense to pull different outcomes back together later and retrain or realign?
Well, what I've done with deployments with my clients is, typically we'll run multiple models in parallel, and we'll basically see how they stack up against each other. I know I'm not directly answering that question, but it's a little bit of a spin off of it. We'll run 3 different scenarios with machine learning and basically training these models in different way. And really what we're trying to get is to figure out which of these models, based upon all of the different sensor inputs, is going to get the highest precision rates and the lowest recall rates. So having them stack ranked against each other and finding a leading horse is typically what we would do. And then over time, we would further, once you find that winner out of your multiple models that you've built, you would further refine and train that one to be the leader. So that's what I've seen as has been the most success. And again, in this particular element, I'm only having one edge component because I'm working on a one asset type of application. But in other ones, there could be other methodologies that people employ.
That's a great point. Dan has a question for you. He wants to know, are there any companies you can think of that are doing amazing things right now with AI that show what's possible?
There's so many. I mean, the AI is being incorporated into just about every technology firm that I've spoken to that's looking for help and go to market. I wouldn't call out any specific to play favorites, but if it isn't a component of what you're building right now, you should be. It offers tremendous cost savings in terms of what your application can do, both in terms of how you build it and the users that are going to utilize it. In most cases, I've seen tremendous ROI, either unlocking new revenue channels because of that solution or dramatically reducing costs.
One more question. Chris wants to know, what have you seen as the biggest hurdles for deploying edge analytics in the field?
Cost. I mean, when you're looking at large industrial IoT deployments, things like a wind turbine can handle the cost associated with a high performance compute at the edge. But some of these other applications, they can't handle a $200, $300, $1,000 or more device. So when we're talking about trucking applications, the bill of materials cost with these little telematics devices that are plugging in can be down as low as $20 or $30. You just don't get that horsepower. So if you want that additional edge processing, it's a big barrier to compare that to traditional telematics devices unless you have a massive ROI. So in some applications that are deployed by the thousands, the hundreds of thousands, or the millions, they cannot afford the same sort of processing power that some lower quantity but higher dollar asset applications can. So that will come down over time. The industry will solve for that. We're already seeing much more compute on edge devices, but cost is going to be something that needs to be driven down for a lot of these very large deployments.
Cool. So my question for you, Christian, and we're running a little bit out of time, but if you had a crystal ball and you were looking at edge computing today, what do you think it's going to look like in a year from now?
A year from now, that not too far away, I think what we're going to see as it relates to predictive analytics is that final category that I was showing on the right-hand side, where the device itself is becoming aware. You're able to run those models out on the edge, and before you're even passing any information back through the cloud, the device is reaching its hand up and saying, there's something wrong with me, order part number XYZ and get me scheduled for repair. I think we're going to start seeing applications that are doing that, which are completely bypassing traditional cloud processing because the models have been refined, the precision rates are there, and the logistical systems are able to handle it.
It's a great look into the not so distant future. Christian, thank you so much for being here today. I really enjoyed your talk as well. Just for everybody's notice, we're going to have a quick break just to get our next speaker lined up. So again, play around on the platform and let us know what you think, and we'll be back shortly. Thank you again, Christian.
Thank you.
Hey everyone, we're back on the main stage. I'm so excited to welcome Nitin Ranjan, Senior Vice President of Edge Products at Building 25. Nitin recently joined the Building 25 team and is passionate about using technology to drive the reskilling and upskilling of the workforce. He empowers humans by designing and implementing edge technologies to bridge critical skills gap. Nitin, thank you so much for being with us today. Just a note, Nitin's going to be talking off camera, but he's there and you'll see his slides shortly. And again, any questions for Nitin, anything related to Edge Technologies or Building 25, put them in the event chat and we'll get to as many as we can once we get into that portion.
All right. You can see my screen, Amber?
You are great. You're good to go, Nitin. Thank you so much.
All right. Thank you, Amber. Welcome, everyone. So let's talk about designing for the edge and how edge computing and lean thinking is positioned to deliver the future in the industrial space. A lot of the contents I'm going to cover today will be something which has been covered by other speakers, John and Christian. So, I'm glad they covered the fundamentals and a lot of the applications. So this should just firm up the applications of edge computing. So cloud alone is ineffective. So in today's industrial space, there is an unprecedented amount of data being generated by these industrial systems. But too often the data are not being used effectively or at all. For example, Forrester reports that between 60 to 73% of all data within an enterprise goes unused for analytics. It's too expensive to collect and process all data in the cloud, and often any insights generated in the cloud are too late for implementation until the scenario presents itself again. Which is why many industrial applications, cloud alone cannot do the job. So what's the trend? Today, around 10% of enterprise-generated data is created and processed outside a traditional centralized data center or cloud. By 2025, this figure will be 75%. So for a very simple use case of edge computing and its relationship to the cloud, consider a driverless car. The car's many sensors and cameras can only have situational awareness if they can respond to what they're seeing in near real time, like trees, other cars, or even people on the road. So self-driving cars will generate as much as 3.6 terabytes of data per hour from clusters of cameras and these sensors. There isn't the time or bandwidth to send the data back to the cloud. Instead, computation must be brought to the edge. And thus, a self-driving car isn't just a next generation car, it's an edge compute node. But even in this straightforward use case, designing and deploying the edge node is just the beginning. So what does edge computing delivers? To me, it provides any machine with a muscle memory. It makes machine situationally aware of its environment and gives the machine the ability to act. For example, when machine is running on full load, it can adjust its own speed to run on half or partial load when it senses that the belts are about to snap or the temperature is drastically increasing. Just responding to its own situation, it can avoid the breakdown. Preventing these downtime is very critical in an industrial space. For example, manufacturers experience an average of 800 hours of downtime every year, making it a $647 billion problem. Even if we design the cloud to ingest all these data, ignoring the cost to do so, we are still compromising the machine learning models because it will run on the noisy, raw industrial data. And then to deal with this noise, additional layer of computation will be needed. This is what I call is a snowball effect resulting in bad outcomes because the fundamental computational design to prevent this machine failure was wrong from the outset. That's why a well-designed edge compute node offers a hyper-efficient complex event processor that cleanses, normalizes, filters, contextualizes, and aligns dirty or raw streaming industrial data as it's produced. Without a complex event processor, latency is higher, the data remains dirty, making analytics much less accurate, and machine learning models are significantly compromised. And again, what computation we need to do at the edge is driven by the use case we are trying to solve and by targeting the correct data closest to its source. Now, as we have established that the edge computing is a core requirement of many discrete industrial use cases, let's talk about what else it delivers. Network of machine learning models is delivered by making every machine an edge compute node. Now, these machines can communicate with each other intelligently. Various edge compute nodes working in tandem can share its computation power, enabling flexible computation design in its implementation. And the aim of lean thinking here is to provide selection criteria of these main techniques that can guarantee the execution of machine learning models on hardware with limited computational power, paving the way to the Internet of Conscious Things. For applications or use cases which involves image recognition or video analysis, fast inference is your key metric. Based on the available hardware like Raspberry or Motorola, we need to select the right technique between CNN or SVM machine learning models while allowing for some acceptable accuracy trade-offs. On the other hand, when accuracy is your key metric, for example, applications surrounding code execution or prediction, we would select from logistic regression or deep neural network techniques. Therefore, it's all about identifying the key metric, the hardware at play, and the use case we are solving for. Implementing powerful deep neural networks on these edge devices is still challenging, and in some circumstances, it is essential to transfer these computation from the edge device to a more powerful edge server on the prem. But while sending data to the edge server, data pre-processing can still be done on these devices. This will reduce redundancy and decrease communication time. And finally, further, we can use techniques like transfer learning, which enables multiple applications to share the common lower layers of deep neural network and only compute higher layers unique to that specific situation. This will further reduce the overall amount of computation. So the developer working on the compute node should look for the right trade-offs between accuracy, latency, and other performance metrics. That's what I call is lean thinking while we empower these compute nodes with machine learning capabilities. Enabling machine learning requires edge plus cloud infrastructure, which is distributed, fast, and flexible, which is why various industrial use cases will require a 5G network. It's predicted that edge and 5G technology together could unlock $740 billion value in manufacturing in 2030. 5G is the enabler that connects the edge and the cloud, relying on data transmission and bandwidth to keep systems smart and functioning. Edge devices generating continuous inferencing on the live streaming industrial data, like audio and video included, regularly send targeted insights back to the cloud. And these edge insights enhance the model retraining and significantly improve its predictive capabilities. The tuned models then push back to the edge in a constant closed loop, reacting quickly to changing conditions and generating much higher quality predictive insights to improve asset performance and process adjustments. Further, in augmented reality and virtual reality applications, creating entirely virtual worlds or overlaying digital images and graphics on top of the real world in a convincing way requires a lot of processing power. Even when phones can deliver that horsepower, the trade-off is extremely short battery life. Edge computing addresses these obstacles by moving the computation into the cloud in a way that it feels seamless. It's like having a wireless supercomputer follow you everywhere, and 5G enables that. In essence, lean code at edge unlocks the value of industrial data. Now, let's summarize a few of the benefits achieved by designing for the edge. First, complex event processing capability for the industrial machines streamlines data volume. Then, by leveraging hybrid infrastructure to deploy edge-to-cloud computing, where data is collected and processed locally on the edge device before select relevant data is sent to the cloud for retraining, further reduces the computational cost. With the help of edge intelligence, organizations can process most of their data locally, eliminating the need to transmit raw, sensitive operational data across networks. And finally, well-designed edge compute nodes should be able to run on existing edge computing devices, further minimizing investment in heavy compute or new industrial control systems hardware. That brings us to the end of my presentation. Thank you all for your time today. Please feel free to get in touch with me. And Amber, let me know if you have any questions from our guest today.
Thank you so much, Nitin. It doesn't look like we have any questions yet, though. I'm going to read what Tom Snyder shared in the chat because I think it's pretty interesting. He says, I predict that the consumption pricing model of cloud computing and communications, pay per amount use transferred, is sunsetting. Edge will drive a new model of outcome-based pricing, fast, accurate, and decision-making. What do you think about that, Nitin?
I couldn't agree more. I think that's very accurate because Now everybody is looking to basically harness all the compute power they have already invested in, using the Industry 4.0 or IoT to get value out of it. And to get value out of it, you've got to focus on discrete, challenging, issues which like hits your bottom line as an organization. So absolutely, I think people are going to harness, and that structure on the cost is going to get tailored towards to more discrete applications on the edge and IoT, and would definitely benefit in getting the outputs they would like to receive from that use case.
Absolutely. I have to say, I really enjoyed the analogy that you used of how edge computing is similar to muscle memory in the body. We had some debate about it on our team as we were talking more about this event, but I really enjoyed that particular part of your presentation. Chris has a question for you. What areas get you most excited around the possibilities? 5G edge compute capabilities, machine learning, or AI? Anything exciting you right now?
Edge computing would lead the way, because, when we talk about smart machines and predictive analytics and things like on that front, what's happening, and when you read my intro, when I talk about skill gaps, the challenge we have here is the data is being generated like in an overwhelming amount. And there is a problem in trying to transfer what's within that data to the current user or the operator in the industrial space to actually make use of it. So I think edge computing really bridges that gap of understanding of the smarter machines with how humans like to make the decision of operation. And I think edge compute bridges that gap for me. And that is why I'm big on human empowerment in terms of decision-making, retraining, upskilling. So edge compute would be my favorite right now.
Awesome. One more. So Tom says, new edge architectures can feel overwhelming to an entrepreneur, much more focused on simple solving a market problem. What is your advice for how an entrepreneur gets started in leveraging these tools?
I always say this, Rome was not built in a day, right? So you have to start somewhere. I have spoken to many of my clients, and their biggest challenge has always been that they have gone through the cycle of digitization, and some people have data lakes, some people have a lot of history of data, but the problem is nobody has been using it because of the absence of computational power or the cost of computation to even historize some of the critical information. And that is why I say pick up your biggest pain point. What is it? It could be as easy as I want to control my inventory. I want to get a better downtime, reduce my downtime, or I want to get a better quality of the product. Just pick the pain point you actually want to solve. And it could be as simple as I want to predict that my machine is going to have health of 30% by X day. Let's see if that's truth or not. And try to implement that alone use case. Because once you have established the fundamental framework, what works within your organization, within your data architecture, I can tell you, it will just be organic after that. You will expand, and that framework will just get reapplied to every other pain points or use cases you might have. And that's how you scale it all the way up to the enterprise.
So you guys heard it first here. Rome was not built in the day. Entrepreneurs, keep it in mind. I think we have one more question from Chris. Nitin, can you think of any consumer level industries not infrastructure? Can you think of any consumer level industries, not infrastructure level? Oh my gosh, guys.
Okay.
Where'd that question go? Sorry, there we go. Okay. Can you think of any consumer level industries, not infrastructure level autonomous cars that could benefit from edge computing?
There are many, what can I say? If you can go into the gaming world, and if you look at even the AR and VR and a lot of the applications over there requires some level of adaptiveness and a quick response in terms of how the game is orchestrated, or even the certain applications within the game features demands in terms of real quick feedback or response time. I think that's where a lot of the AR and VR experiences has been dumped upon the shoulders of edge computing to further improve the throughput and reduce the latency in those applications.
Awesome. Well, Nitin, thank you so much for being here today. It looks like our questions have stopped for now, but really, really thank you. We've all enjoyed your presentation so much, and congratulations on the new position at Building 25. Everyone else, we're going to take another short break, and then we're going to come back one more time for a surprise announcement from our friends over at SAS. So again, check out the platform, test out some of its features, and we'll see you guys in about 5 minutes. Nitin, thank you again.
Thank you, Amber. Thank you, everyone.